Hey guys, here I am. I'm back. Let me continue. The first argument of fopen is the name of the file is a character string. The second argument is a mod. Is also is a character string which indicates how one intends to use the file. Allowable mods are read parenthesis double quote r, write parenthesis double quote w, or append parenthesis double quote a. If you open a file which does not exist for writing or appending, it is created if possible. Opening an existing file for writing causes the old contents to be discarded. Trying to read a file that does not exist is an error. And there may be other causes of error as well, like trying to read a file when you don't have permission. If there is any error, fopen will return the null pointer value null, which for convenience is also defined in stdio.pointEdge. The next thing needed is a way to read or write the file once it is open. There are several possibilities, of which gets and puts are the simplest. Gets returns the next character from the file. It needs the file pointer to tell it what file. Thus, C equal gets parenthesis fp places in C the next character from the file referred to by fp and EOF when it reaches end of file. Puts is the inverse or reverse of getC. Puts the character C on the file fp and returns C like getChar and putChar. getC and putC may be macros instead of functions. When a program is started, 3 files are opened automatically and file pointers are provided for them. These files are the standard input, the standard output, and the standard error output. The corresponding file pointers are called string, stout, and stir. stdin, stdout, and stde error. Normally, these are all connected to the terminal, but stdin and stdout may be redirected to files or pipes are described in section 7.2. getChar and putChar can be defined in terms of getC and putC, stdin and stdout as follows. For formatted input or output of files, the functions fscanf and fprintf may be used. These are identical to scanf and printf, save that the first argument is a file pointer that specifies the file to be read or written. The control thing is the second argument. With these preliminaries out of the way, we're now in a position to write the program cat to concatenate. We're now in a position to write the program cat to concatenate files. The basic design is one that has been found convenient for many programs. If there are command line arguments, they are processed in order. If there are no arguments, the standard input is processed. This way, the program can be used standalone or as part of a larger process. The file pointers stdin and stdout are predefined in the i/o library as the standard input and standard output. They may be used anywhere an object of type file asterisk can be. There are constants, however, not variables, so don't try to assign to them. The function fclose is the inverse of fopen. It breaks the connection between the file pointer and the external name that was established by fopen, freeing the file pointer for another file. Since most operating systems have some limit on the number of simultaneously Since most operating systems have some limit on the number of simultaneously open files that a program may have, it's a good idea to free things when they are no longer needed. As we did in CAD, there is also another reason for fclose on an output file. It flushes the buffer in which put C is collecting output. Fclose is called automatically for each open file when the program terminates normally. 7.7 Error handling, std error and excite. The treatment of errors in CAD is not ideal. The trouble is that if one of the files can't be accessed for some reason, the diagnostic is printed at the end of concatenated output. That is acceptable if that output is going to a terminal, but bad if it is going into a file or into another program via a pipeline. To handle this situation better, a second output file called stderr is assigned to a program in the same way that stdin and stdout are. If at all possible, output written on stderr appears on the user's terminal even if the standard output is redirected. Let us refresh CAD to write its error messages on the standard error file. The program signals errors two ways. The diagnostic output produced by fprintf goes on to stderr, so it finds its way to the user's terminal instead of disappearing down a pipeline or into an output file. The program also uses the standard library function excite, which terminates program execution when it is called. The argument of excite is available to whatever process called this one. So the success or failure of the program can be tested by another program that uses this one as a subprocess. By convention, A return value of 0 signals that all is well, and various non-zero values signal abnormal situations. Exit cause fclose for each open output file to flush out any buffered output. This calls a routine named _exit. The function _exit causes immediate termination without any buffer flushing. Of course, it may be called directly if desired. 7.89 input and output. The standard library provides a routine fgs, which is quite similar to the getLine function that we have used throughout the book. The call, like this, reads the next input line, including the new line, from file fp into the character array line. At most, max line -1 characters will be read. The resulting line is terminated with \0. Normally, fgs returns 9. On end of file, it returns null, or getLine returns the line length and 0 for end of file. For output, the function fputs writes a string which need not contain a new line to a file. Fputs line parenthesis line fp to show that there is nothing magic about functions like fgs and fputs. Here they are, copied directly from the standard isnational library. Exercise 7 mid-score 3. Write a program to compare two files, pointing the first line and character position where they differ. Exercise 7 mid-score 4. Modify the pattern finding program of chapter 5 to take its input from a set of named line files, or if no files are named, as arguments from the standard input. Should the file name be printed when a matching line is found? Exercise 7 mid-score 5. Write a program to print a set of files, starting each new one on a new page, with a title and a running page count for each file. 7.9. Some miscellaneous functions. Some miscellaneous functions. The standard library provides a variety of functions, a few of which stand out. The standard library provides a variety of functions, a few of which stand out as especially useful. We have already mentioned the string functions string, struct_by, struct_pi, struct_add, and strcmp. Here are some others. Character class testing and conversion. Several macros perform character tests and conversions. I don't know what is it. Okay, fine. The standard library provides a rather restricted version of the function engage, which we wrote in chapter 4. It is called engage_c. Pushes the character C back onto file fp. Only one character of pushback is allowed per file, and getC may be used with any of the input functions and macros like scanf, getC, or getChar. System call. The function system executes the command contains in the character string s, then resumes execution of the current program. The contents of s depend strongly on the local operating system as a trivial example on Unix, the 9. Like this, causes the program date to be run. It prints the date and time of day. Storage management. The function clog is rather like the log we have used in previous chapters. Returns a pointer to enough space for an object of the specified size or null. If the request cannot be satisfied, the storage is initialized to 0. The pointer has the proper alignment for the object in question, but it should be cast into the appropriate type, as in C3. Freeze the space pointed to by P when P is originally obtained by a call to clog. There are no restrictions on the order in which space is freed, but it is a ghastly error to free something not obtained by calling clog. Chapter 8 shows the implementation of a storage allocator like clog, in which allocated blocks may be freed in any order. Here we come Chapter 8. Chapter 8, the Unix system interface. Unix. Does someone use it? What the hell? I don't use it. The material in this chapter is concerned with the interface between C programs and the Unix operating system. Since most C users are on Unix systems, this should be helpful to a majority of readers, even if you use C on a different machine. However, you should be able to glean more insight into C programming from studying these examples. The chapter is divided into 3 major areas: input/output file system and a storage allocator. The first 2 parts assume a modest familiarity. The first two parts assume a modest familiarity with the external characteristics of Unix. Chapter 7 was concerned with a system interface that is uniform across a variety of operating systems. On any particular system, the routines of the standard library have to be written in terms of the I/O facilities actually available on the host system. In the next few sections, we will describe the basic system entry points for I/O on the Unix operating system, and illustrate how parts of the standard library can be implemented with them. 8.1 File Descriptors. In the Unix operating system, all input and output is done by reading or writing files because all peripheral devices, even the user's terminal, are files in the file system. This means that a single homogeneous interface handles all communication between a program and peripheral devices. In the most general case, before reading or writing a file, it is necessary to inform the system of your intent to do so. a program called opening the file. If you are going to write on a file, it may also be necessary to create it. The system checks your right to do so. Does the file exist? Do you have permission to access it? And if all is well, returns to the program a small positive integer called a file descriptor. Whatever I/O is to be done on the file. File descriptor is used instead of the name to identify the file. This is roughly analogous to the use of read and write in Fortran. All information about an open file is maintained by the system. The user program refers to the file only by the file descriptor. Since the input and output involved in the user's terminal is so common, special arrangements exist to make this convenient. When the command interpreter, the shell, runs a program, it opens 3 files with file descriptors 0, 1, and 2 called the standard input, the standard output, and the standard error output. All of these are normally connected to the terminal. So, if a program reads file descriptor and writes file descriptors 1 and 2, it can do terminal I/O without worrying about opening the files. The user of a program can redirect I/O to and from files with angle break, left angle break, and right angle break. In this case, the shell changes the default assignments for file descriptors 0 and 1 from the terminal to the named files. Normally, file descriptor 2 remains attached to the terminal, so error messages can go there. Similar observations hold if the input or output is associated with a pipe. In all cases, it must be noted the file assignments are changed by the shell, not by the program. The program does not know where its input comes from nor where its output goes, so long as it uses file 0 for input and 1 and 2 for output. 8.2 Low-level I/O read and write. The lowest level of I/O in Unix provides no buffering or any other service. It is in fact a direct entry into the operating system. All input and output is done by 2 functions called read and write. For both, the first argument is a file descriptor. The second argument is a buffer in your program where the data is to come from or go to. The third argument is the number of bytes to be transferred. Calls are like this. Each call returns a byte count, which is the number of bytes actually transferred. On reading, the number of bytes returned may be less than the number asked for. A return value of 0 bytes implies end of file, and -1 indicates an error of some sort. For writing, the returned value is the number of bytes actually written. It is generally an error if this is equal to the number supposed to be written. The number of bytes to be read or written is quite arbitrary. The 2 most common values are 1, which means 1 character at a time and buffered, and 512, which corresponds to a physical block size on many peripheral devices. This later size will be most efficient, but even character at a time snapshot is not inordinately expensive. Putting these facts together, we can write a simple program to copy its input to its output, the equivalent of the file copying program written for Chapter 1 in Unix. This program will copy anything to anything, since the input and output can be redirected to any file or device. If the file size is not a multiple of buffer size, some read will return a smaller number of bytes to be written by write. The next call to read after that will return 0. It is instructive to see how read and write can be used to construct higher level routines like getChar, putChar, etc. For example, here is a version of getChar which does unbuffered input. C must be declared char because read accepts a character pointer. The character being returned must be masked with 0377 to ensure that it is positive, otherwise sign extension may make it inactive. The constant 0377 is appropriate for the PDP left but not necessarily for other machines. The second version of getChar does input in big chunks and hands out the characters one at a time. Open, create, close, unlinked. Other than the default standard input, output, and error files, you must explicitly open files in order to read or write them. There are two system entry points for this, open and create. Open is rather like the fopen discussed in Chapter 7, except that instead of returning a file pointer, it returns a file descriptor, which is just an int. As with the fopen, the name argument is a character string corresponding to the external file name. The access mode argument is different. However, read mode is 0 for read, 1 for write, and 2 for read and write access. Open returns -1. If any error occurs otherwise, it returns a valid file descriptor. It is an error to try to open a file that does not exist. The entry point create is provided to create new files and to rewrite old ones. Returns a file descriptor if it was able to create a file called name and -1 if not. If the file already exists, create will truncate it to zeroness. It is not an error to create a file that already exists. If the file is brand new, creates it with the protection mode specified by the pmode argument. If the Unix file system, there are 9 bits of protection information associated with the file, controlling read, write, and execute permission for the owner of the file, for the owners group, and for all others. Thus, a 3-digit octal number is most convenient for specifying the permissions. For example, 0755 specifies read, write, and execute permission for the owner, and read and execute permissions for the group and everyone else. To illustrate, here is a simplified version of the Unix Autodidactism, a program which copies one file to another. The main simplification is that our version copies only one file and does not permit the second argument to be a directory. There is a limit typically 15 to 25 on the number of files which a program may have open simultaneously. Accordingly, any program which intends to process many files must be prepared to reuse file descriptors. Routine close breaks the connection between a file descriptor and an open file, and frees the file descriptor for use with some other file. Termination of a program by exit or return from the main program closes all open files. Function and inc file name removes the file name from the file system. So exercise 8 middle score 1. Rewrite the program cat from chapter 7 using read, write, open, and close instead of their standard library equivalents. Perform experience to determine the relative speeds of the two versions. 8.4 Random access seek and lseek. File I/O is normally sequential. File ISO is normally sequential. Each read or write takes place at a position in the file right after the previous one. When necessary, however, a file can be read or written in any arbitrary order. System can lseek provides a way to move around in the file without actually reading or writing. Forces the current position in the file whose descriptor is fd to move to position offset, which is taken relative to the location specified by origin. Subsequent reading or writing will begin at that position. Offset is a long fd and origin are ends. Origin can be 0, 1, and 2 to specify that offset is to be measured from the beginning, from the current position, or from the end of the file respectively. For example, to append to a file, seek to the end before writing. To get back to the beginning, rewind. Notice the 0L argument. It could also be written as parenthesis long 0. With lseek, it is possible to treat files more or less like large arrays at the price of slower access. For example, the following simple function reads any number of bytes from any arbitrary place in a file. In pre-version 7 Unix, the basic entry point to the I/O system is called seek. Seek is identical to lseek, except that its offset argument is an int rather than long. Accordingly, since PDP-11 integers have only 16 bits, the offset specified for seek is limited to 65535. For this reason, origin values of 345 calls seek to multiply the given offset by 512, the number of bytes in one physical block, and then interpret origin as if it were 0, 1, 2 respectively. Thus, to get to an arbitrary place in a large file requires two seeks. First one which selects the block, then one which has origin equal to 1 and moves to the desired byte within the block. Exercise 8 middle score 2. Clearly, seek can be written in terms of lseek and vice versa. Write each in terms of the other. 8.5 Example. An implementation Example, an implementation of fopen and getC. Let us illustrate how some of these pieces fit together by showing an implementation of the standard library routines fopen and getC. Recall that files in the standard library are described by file pointers rather than file descriptors. A file pointer is a pointer to a structure that contains several pieces of information about the file. A pointer to a buffer so the file can be read in large chunks. A count of the number of characters left in the buffer. A pointer to the next character position in the buffer. Some flags describing read/write mode, etc. and the file descriptor. The data structure that describes a file is contained in the file studio .h, which must be included by #include in any source file that uses routines from the standard library. It is also included by functions in that library. In the following export In the following excerpt from not expert excerpt in the following excerpt from studio.h names, which are intended for use only by functions of the library, begin with an underscore, so they are less likely to collide with names in a user's program. Like this. What does export? I don't know. The getC macro normally just decrements the count, advances the pointer, and returns the character along hash defined as continued with a \. If the count goes negative, however, getC calls the function underscore fieldbuff to replenish the buffer, reinitialize the structure contents, and return a character. A function may present a portable interface, yet itself contain non-portable constructs. getC masks the character with 0377, which defeats the sign extension done by the PDP11 and ensures that all characters will be positive. Although we will not discuss any details, we have included the definition to PutC to show that it operates in much the same way as getC, calling a function underscore large buff when its buffer is full. Function fopen can now be written. Most of fopen is concerned with getting the file opened and positioned at the right place and setting the flag bits to indicate the proper state. fopen does not allocate any buffer space. This is done by underscore fieldbuff when the file is first read. Like this, where the function underscore fieldbuff is rather more complicated. The main complexity lies in the fact that underscore fieldabove attempts to permit access to the file even though there may not be enough memory to buffer the initial. If space for a new buffer can be obtained from clog, all is well. If not, underscore fieldabove does unbuffered initial using a single character stored in a private array. All this code is not what we should focus now. The first call to get C for a particular file finds a count of 0, which forces a call of underscore fieldabove. If underscore fieldabove finds that the file is not open for reading, it returns EOF immediately. Otherwise, it tries to allocate a large buffer, and following that, a single character buffer, setting the buffering information in underscore flag appropriately. Once the buffer is established, underscore fieldabove simply calls read to fill it, sets the count and pointers, and returns the character at the beginning of the buffer. Subsequent calls to underscore fieldabove will find a buffer located. The only remaining loose end is how everything gets started. Array underscore IOB must be defined and initialized for stdin, stdout, and stderr. The initialization of underscore flag part of the structure shows that stdin is to be read, stdout is to be written, and stderr is to be written and buffered. Exercise 8, middle score 3, rewrite f open and underscore fieldabove with fields instead of explicit bit operations. Exercise 8, middle score 4, design and write the routines underscore flush buff and f close. Exercise 8, middle score 5, the standard library provided is a function. Which is identical to lseek, except that fp is a file pointer instead of a file descriptor. Write fseek. Make sure that your fseek coordinate is properly with the buffering then for the other functions of the library. 8.6 example, listing directories. A different kind of file system interaction is sometimes called for determining information about a file, not what it contains. The Unix command ls list directory is an example. It prints the names of files in a directory, and optionally other information such as sizes, permissions, and so on. Since on Unix, at least the directory is just a file, there is nothing special about a command like ls. It reads a file and picks out the relevant parts of the information it finds there. Nonetheless, the format of that information is determined by the system, not by a user program. So ls needs to know how the system represents things. We will illustrate some of this by writing a program called fsize. Fsize is a special form of ls which prints the sizes of all files named in its argument list if one of the files is a directory. Fsize applies itself recursively to that directory. If there are no arguments at all, it processes the current directory. To begin a short review of file system structure, a directory is a file that contains a list of file names and some indication of where they are located. The location is actually an index into another table called the inode table, and the inode for a file is where all information about a file except its name is kept. A directory entry consists of only two items: an inode number and the file name. The precise specification comes by including the file sys/dir.h, which contains, like these words, the type inode _t _t is a type div describing the index into the inode tab. It happens to be unsigned on PDP 11 Unix, but this is not the sort of information to embed in a program. It might be different on a different system. Hence, the type div, a complete set of system types, is found in sys/types.h. The function stat takes a file name and returns all of the information in the inode for that file. That is, fills the structure stubs with the inode information for the file name. The structure describing the value returned by stat is in sys/stat.h and looks like this. Most of these are explained by the command fields. The st_mode entry contains a set of flags describing the file. For convenience, the flag definitions are also part of the file, as well as /stat.h. Now we are able to write the program fsize if the mode obtained from stat indicates that a file is not a directory. Then the size is at hand and can be printed directly. If it is a directory, however, then we have to process that directory on file at a time. It in turn may contain subdirectories, so the process is recursive. The main routine, as usual, deals primarily with command line arguments. It hands each argument to the function fsize in a bigger buffer. Function fsize prints the size of the file. If the file is a directory, however, fsize first calls directory to handle all the files in it. Note the use of the flag names as _fmate and as _ifdir from stat.h. Okay, guys, I'm thirsty. I need a cup of good tea. See ya.